You know, it feels completely ordinary, right? But it secretly dictates the shape of the entire universe around us. Today, we're looking at the simple act of lines crossing and how those tiny, everyday intersections actually create the invisible, unbreakable mathematical rules of our world. Geometry is highly cumulative. It doesn't just spontaneously happen out of nowhere. It all starts with one fundamental event: what happens when lines and curves cross paths in space.
Okay, let's dive into this. Here's our roadmap for this explainer. We're going to start with the magic of intersections, then move into decoding parallel lines, identifying angle pairs, the rules of triangle construction, and finally, we'll wrap up with the triangle inequality theorem. Let's get into it.
Section 1. The magic of intersections, where mathematical rules are born.
Moving right along to Section 2, decoding parallel lines. Enter the transversal.
So our first major geometric player is the transversal. That's basically just that diagonal line you see slicing right through a perfectly matched set of parallel horizontal lines. By simply crossing those parallel lines, it creates a whole new world of angles. To make sense of it, you really just need to orient yourself with the zones. Notice the interior zone. That's the space trapped directly between the two parallel lines, and then you have the exterior zones, which are the wide open spaces on the outside top and outside bottom. If you've ever looked up at the steel trusses of a bridge or the framing of a roof, you're literally looking at transversals hard at work.
Now, because the transversal cuts straight through perfectly parallel lines, this single intersection creates two distinct buckets of rules. Literally every single angle pair created falls into one of two categories. Either they're congruent angles, meaning they are identical twins with the exact same measurement, or they're supplementary angles. That means they don't match, but they join forces to add up to perfectly 180 degrees, creating a straight half-circle line.
Section 3, identifying angle pairs and spotting the visual patterns.
First up, we've got alternate interior angles. Imagine for a second being trapped inside those two horizontal parallel lines. Now place one angle on the left side of that slicing transversal and the other on the right side. Because the horizontal lines are perfectly parallel and straight, these alternating interior angles are always congruent. They are mathematically identical, no exceptions. And this brilliantly illustrates exactly where those alternate interior angles live. You can visibly see they're trapped in that interior zone, on opposite sides of the cutting line. Regardless of the angle of the transversal, no matter how steep or shallow it is, as long as those top and bottom lines are parallel, those alternating spaces are exactly the same size.
Now contrast that with same-side interior angles. These are still trapped inside the interior zone, but now they're clumped together on the exact same side of the transversal. Because one is wedged into a sharp, acute corner and the other is opened up into a wider, obtuse corner, they clearly don't match. Instead, well, they complete each other. They're supplementary, meaning if you add them together, they will always equal exactly 180 degrees.
Okay, here's a rule that breaks out of just parallel lines: vertical angles. When any two straight lines intersect anywhere in the universe, the angles that are directly across from each other form a pair of vertical angles. Think of them kind of like an open pair of scissors. If you open one side wider, the opposite side perfectly mirrors it. They are always perfectly congruent. Now, what's really interesting about this is how these relationships give us a mathematical master key. Because we know these rules, whether angles are congruent or supplementary, knowing just one single angle measurement unlocks the entire geometric puzzle. Like, if a vertical angle is 120 degrees, the one across from it is absolutely guaranteed to be 120 degrees. It's just an unbroken chain of logic.
Moving to Section 4, Rules of Triangle Construction, using intersecting circles to build shapes.
So how do we guarantee that three random lines will actually form a triangle? Well, we use intersecting circles. First, you lay down the longest side of your proposed triangle, like a flat foundation. Let's say it's 8 centimeters. Next, you take your two shorter sides, say 4 and 5 centimeters, and you use those exact lengths to draw circles originating from either end of your foundation. Think of these smaller sides as physical swinging hinges. Finally, you just look to see exactly where those two swinging circles intersect in the empty space above your foundation.
Let's move to Section 5 and see how this builds into the triangle inequality theorem. Basically, what happens when intersections fail?
This is the ultimate mathematical decider right here. Ask yourself, what happens if the circles drawn from the base just never reach each other? Imagine the physical failure of this construction.
You've laid out your long foundation, you swing your two smaller sides on their hinges, but they're just simply too short. They swing through the air, completely missing each other. As the source material lays out, there are really only 3 possible outcomes when you try this. Outcome 1. The circles intersect at 2 distinct points. This means the sum of your 2 smaller radii, like 4 plus 5, is 9, which is strictly greater than your base of 8. They reach past the middle and overlap. Boom, a triangle is born. Outcome 2. The circles just barely touch at 1 single point. Their sum equals the base perfectly. When this happens, the lines just collapse flat on top of the base. No triangle. And outcome 3. The circles do not intersect at all. Their sum is less than the base. There's no connection in the air. So, no triangle.
So, the crucial point is this: the triangle inequality theorem. For a closed triangle to exist in our universe, the sum of the lengths of any 2 of its sides must be strictly greater than the length of that third side. Without that overlap, without that physical intersection of the swinging radii, you just don't get that necessary third point in space to form the vertex. The shape just cannot close.
Which brings us to our final thought. We've seen how simple straight lines crossing create unbreakable rules for congruent and supplementary angles, and how curves crossing dictate whether a shape is even allowed to exist at all. So if geometry is really just the study of where lines and curves successfully intersect, what other impossible shapes are hiding in plain sight, just waiting for their rules to be discovered? Keep looking for the intersections around you, and thanks so much for joining me for this explainer.